Welcome to the S2 Cognition Podcast. S2 is the official cognitive evaluation in sports, from youth to pro, where athletes and coaches build to win.
Dr. Geoffrey Woodman rejoins the S2 Cognition Podcast today. As you'll remember, he's a professor at Vanderbilt University in psychology and neuroscience, and he's the director of the Vanderbilt Vision Research Center. Dr. Woodman has published over 100 peer-reviewed papers and 2 textbooks on vision and visual cognition, and is considered a leading expert in attention and visual perception. Today, we are going to dig into S2 Cognition's perception speed task and how it relates to sports. All of that is coming up here on the S2 Cognition Podcast, and as always, please subscribe, leave a review, and share this podcast with a friend. Up next, Dr. Geoffrey Woodman. Dr. Jeff, thanks for rejoining us again for another topical and educational discussion on the visual system. We touched on search efficiency this time we're going to look at perception speed. I want to first start and go to Brandon real quick. Brandon, can you describe what task we use and with the athletes sit down and take the evaluation, they take perception speed. What is it that they take?
Yeah, good question. And I would say, this is probably the most question we get from coaches and athletes is, what is perception speed? What does it mean? What does that mean to perceive things quickly? How is there variability between people? So Scott and I actually picked a task that shows a lot of variability and has a lot of precision in the timing in which it takes to perceive something. So we use just a classic sort of masking paradigm in which we show a stimulus on the screen. It's missing a corner. You have to identify which corner is missing. And it's masked, and we changed the amount of time that it's between the stimulus and the mask to see how long or how much information that they need to be able to perceive it. Does that make sense?
Yeah, and so when we're talking about this, can you describe basically what are we hoping to glean? What do we want to understand by this task? What's the hope? And when athletes take this and they take the evaluation for perception speed, what do we hope to get from that?
So we want to know how quickly it takes someone to perceive visual information in their central point of focus. And so when you think about a baseball player, you start thinking about pitch recognition. You start thinking about these guys who can pick up spin. You hear about guys who can tell, hey, if the ball has a red dot on it, it means it's this pitch. If it's a solid red, it means it's this pitch. And so they can actually pick up on very subtle visual details that most of us can't. To give them information on what pitch it is. In football, at the line of scrimmage, the game happens so quickly, you need to have a quick sort of camera shutter speed, if you will, to be able to pick up on all the visual information that's going on. Quarterbacks seeing tight passing windows, you got to be able to perceive things very quickly and then act on them very quickly. So we're hoping that our evaluation, I think we have enough data to suggest that, especially in baseball, that we are capturing how quickly guys can pick up information and then make sense of it.
So how quickly people are processing at the point of focus is essentially what we're trying to measure. Yeah, how would we say that athletes differ from, the average human population? Can we understand what the human population is doing when they have to take this task versus what athletes do when they take it?
So, and this is definitely getting into Jeff's realm. We have seen, professional baseball players perceive things within 15 or 16 milliseconds. That's like 16 1,000th of a second, where at one point we thought that this was actually subliminal, that humans couldn't process visual information that quickly. And we have pro baseball players who can actually get everyone correct with just a 16 millisecond SOA. And these guys can see things that are occurring at 95, 100 miles an hour, where just the average Joe, it's just not possible. And to be quite frank, and I know Scott, who lives in the baseball world, gives this example all the time. Folks love to talk about vision, right? And these pro baseball players have 20/10 vision, and that's what makes them be able to see things and are good hitters. But quite frankly, like Scott says, there's millions of people walking around with 20/10 vision, and they can't hit 95 miles an hour, right? So there's a lot of visual processing that occurs once your eyes actually see the visual information. So you have to be able to perceive all of that information and utilize it for future action.
Hey, Brandon, let me just add a little something to that. That's a perfect description. This becomes really important because what we're essentially saying is you can flash an image for 16 one-thousandths of a second, and some human processors can process that short flash to the point of recognizing what they saw, which is pretty incredible. Other athletes, though, may need 80 milliseconds of that flash to be, 5 times longer before they can consistently recognize what they see. And when you're talking about a difference in athletes, tens of milliseconds up to maybe a tenth of a second, 100 milliseconds, for a baseball player, that's significant because they have less than 380, 90 milliseconds to recognize what pitch it is, where it's moving in space, to organize their motor system, to decide whether to swing, and if they decide to swing, when to swing, where to swing. We're talking tens of milliseconds become significant to the whole process of these decisions that athletes have to make. I think it's helpful to kind of
it's wild.
the range.
Absolutely.
Yeah.
To make that distinction, I think it's really important to talk about the difference. I know we've talked about this before, so I would love really all three of you to jump in with your opinions on this. What is the difference between vision and visual processing, and especially when it comes to perception speed?
Yeah, Jeff, this is your wheelhouse. You want to take this?
Sure. I'm teaching the visual system course at Vanderbilt this semester, so I better be able to answer this, I guess. So, when the big difference there is something Scott already mentioned, which is the recognition of the object. That's really kind of the key thing that psychologists distinguish between your visual system running and working versus you actually knowing what you see. If we were to anesthetize Brandon and prop open his eyes with an operculum so that he had the full Clockwork Orange thing going, what we could see is that his visual system would actually still be responding to the stimuli we flash with the same latency all the time. Whether he happens to be close to coming out from anesthesia or not, if his heart was beating really fast at that time or not, it looks like it's kind of somewhat constant. But then if he were not under anesthesia, if he were conscious and trying to say whether the thing he's seeing is a digit or a letter, and he just has to make that simple distinction between whether it's 1 through 9 versus A through Z. When he now has to do that task, it looks like that the amount of time he now needs to recognize the object is somewhat variable from trial to trial. So if we have him press a button to say, when can you recognize this object, you'll actually see variability even at the individual subject level from trial to trial, because it looks like that the neurons, like in your visual system, are responding to the object at the same time, but you haven't had this magic thing happen. And that magic thing of recognizing the objects does appear to vary pretty drastically in terms of speed across people. But the other thing that all humans have is the ability to recognize objects at an expert level that's just bananas relative to supercomputers. So this has actually been the thing that has made humans remain in control of the Earth until now, is that our visual systems have been the fastest supercomputer known to humans. We've been able to recognize objects that, in fact, like rooms full of computers still are just barely able to do. And the current artificial intelligence methods, let's call them, or the architecture that people are using to have like the Tesla drive the car and that sort of stuff, are just the visual system. They're models of what we've understood about the visual system. And if you plug that into your code, it's smart. So it looks like the very architecture that's processing these things is fairly remarkable in that it looks like, being able to recognize objects may actually be kind of intelligence. That it's what we're calling intelligence. So, the artificial intelligence that Google has can tell you if there's a kitty cat in this image. And in 1975, Molly Potter at MIT showed that the average person needs about 80 milliseconds to say whether this picture contained a cat in it or not. So it looks like the average person can do that really fast. So when I try to tell my students about, okay, we're going to talk about how your brain figures out what this is, this pencil. How does your brain know this is a pencil? And people are like, whoa, this class got stupid real fast, because it doesn't feel like this is a hard task for our brains. For our brains, that's trivial. And babies can do it incredibly easy. There may even be, you can do some in utero distinctions between tones and light flashes and stuff. So the stuff is very early in our visual systems. So it's not like, it seems to be fundamental to something that makes us who we are, what we do. So it's a really interesting thing. The first review paper that I'm aware of that reviewed what we knew about masking using the kind of task that you guys use here was written in 1929. So using masks to study the speed of visual processing, the speed of visual recognition, has been done for an incredibly long time.
And that's a great segue. I love that you brought that, because I want to talk about, once we understand the human and the athlete limitations of where we're trying to go with this, and our task that S2 Cognition uses, what are some of the, if you're looking at it without knowing what our task is, what are some buzzwords that we might hear, Scott, Brandon, in the sports world of perception speed? When people say this, they're talking about perception speed. What are those in those sports?
I want to get Jeff to elaborate on one thing before
Let's do
we
it.
go to that,
Let's do
because
it.
I think it's relevant, because I think it's related to the terms we use. We often confuse what the eye does with what the brain does. And Jeff just kind of said that, if I heard him correctly, the eyes are pretty constant in how they receive information and transmit that information to the brain. And the bulk of the variability, the person to person, athlete to athlete differences, are going to be in how the brain takes that information from the eyes and then processes it to the point of recognizing what it is. That was the main thrust of that point there, right? What the eyes are doing is pretty constant. The brain's doing. That's where the meat of the timing differences are going to be revealed.
Exactly right. And it may even be that the earliest stages of the brain kind of are more machine like that, in that it's always, right at 40 milliseconds that they fire their action potentials and say, the stimulus is here. And that it's really like a machine, and that it looks like it may actually be these kind of higher level areas that do problem solving and creativity and those sort of things that are really required for us to be aware that the object's there. So it's interesting that when we talk about, perception speed, it's kind of awareness speed. It's how fast can you become aware of the object that you're seeing. Then this gets us into a more philosophical land of what is consciousness and all that kind of stuff. But it is related, and so Scott's point is dead on. This is related to consciousness, and how do you know the thing is seeing the thing it's seeing?
Even in the brain, there are cells in the primary visual processing cortex of the brain that are devoted to motion or color or different configurations. And it's a build up process to the point where, more complicated systems are integrating that information to get to that. What is it? What pitch is it? What just happened? Did that defender move left or right? Did that window open up for me to execute a pass or a play? And so that specialization at the lowest level, we are talking about recognizing things as a key distinction between perception speed and just say visual speed, because we get that. I think the terms, back to Harrison's question, Brandon, you've heard these, more of these probably than I do, but the person diagnoses the situation quick. Embedded in that is a little bit of, they visually see and recognize what's happening faster. They're a tick quicker, off the ball or in their again, diagnosing something. I think that's what we're really talking about, is they see it faster.
Yeah, Jeff, as you probably know, we have three different visual tasks in our football battery, perception speed being one of them. We had a linebacker at one of our NFL teams who had low perception speed, but had other good visuals. And they used to use him on the outside and they would bring him up to the line. They said his performance was significantly better when they put him one step back, just one step back. Does that make sense to you? I mean, if his perception speed is low, we're assuming he's slow to recognize things, he's slow to process things. So a step back just gives him a little bit more time to diagnose and to recognize what's going on, to then inform his actions.
Yeah, I think that's a great interface between what you guys can provide in terms of providing these metrics about how their brain's functioning, and then coaching, which is how can you just tweak the alignment a little bit to then have it all work together. I think that's a great example.
So Harrison, going back to your question, we do hear the game speed is just too fast for this guy. Or he's just, his first step is slow. Those kinds of things that are getting at, that piece of processing. Jeff, we may not have, this may be a deeper discussion or things like that, but in that mechanical sort of phase, in that processing phase, are there some common barriers? Are there some common things that might cause one to process information slow? Or is it just not that black or white?
Well, there's one big thing. Okay, there are some black and white things, but there's not a ton, right? It's mostly gray. Psychology is the field of grayness, but we're starting to see slightly better forms. For example, one of the things that's clearly detrimental is having attention focused elsewhere. So if you're focusing on a location in space and then dots are coming up, and you're supposed to judge when those come up, the ones that come up where you're paying attention appear to come on faster. So attention can modulate exactly these sorts of exactly the sort of thing we're talking about, which is how do I recognize the objects? It looks like the object appears in your visual stream faster if you're attending to that location. So if you're a hitter who's keeps trying to see if the first base coach is tipping the pitch or something other silly, let's say, strategy like that, that's really going to hurt you because you're not going to be getting the best information possible. So where you focus spatial attention is incredibly critical.
I may be taking us off course here, and Scott, I know you deal with this world all the time, but when we talk about pitch recognition, we've often heard this hard focus versus soft focus. This where you attend. Do you try to attend to the pitcher's hand? Do you try to attend to release? All of those sorts of things. Is it as simplistic as that? I mean, do we have this hard focus, soft focus that we can go in and out of? Is there anything that is helpful, I guess, to recognize that pitch?
Yeah. And what are the trade-offs? Right.
Well, I mean, I can tell you that in the laboratory, the biggest thing we know of is learning. Learning can crush all of these problems, if you want to call them that. So, I mean, I had the most extreme example because I worked with non-human primates and I was doing a masking experiment with monkeys. Now, the interesting thing about monkeys is their whole job is to do this masking experiment. They're not trying to make the Hall of Fame. So they have a much easier job, which is like, I'm going to see which way that gap is on that diamond, baby. And so they would do that all day for months, is how long I had to train some of these monkeys. Well, once the monkeys kind of figured out the task, and once I got them so that they could do it in about a human range, well, they kept getting better and better across days that they kept doing this thing, and they kept getting better and better. And then it became a huge problem because these monkeys were seeing the object so quickly, it was faster than any human could do it. So we were putting up arrays of objects, and they had to decide whether there was a T tilted in a certain direction in this array. And we flashed it up there for one frame. which was 16 milliseconds. That was the shortest that this monitor would let us show it.
Sure.
So we would flash it, follow it with masks, and the monkey could do it at 80% correct. And
Wow.
Unfortunately, we don't have any human analog to that. So what we were in the business of trying to study interesting things in the human brain, but using monkeys. So the idea is train them to do a task that a human can do. Then you can record from inside the brain and see how they're doing it. Well, we could have recorded from the super monkeys, I guess, and found out what a super brain does. That's like 10 times better than our own brain. But the truth is we can probably build that into ourselves. If we were willing to do the same number of trials the monkeys were willing to do, you probably can make your visual system just screaming fast and be able to recognize objects incredibly
Really?
fast. I
Wow.
totally think so. The only data
Okay,
points I have,
what kind of hours are we looking at here, Jeff? I mean,
we're talking your livelihood depends on it kind of hours, which I understand athletes feel that way about their task and everything. But I mean, so the data points I have are kind of myself and some other graduate students. So the people who program up these experiments are us. So we look at the stimulus for hours to try to make sure everything's right, and then we practice it on ourselves, and we kind of run it on ourselves to see if it's working. And we have to know it well enough that we can detect errors in the code that like the computer program showed that for too long. That wasn't as short
right.
as it was supposed to be. You need to be able to detect those things.
Ryan Wiley type stuff.
Yeah, no joke.
Well, yes. And so then the thing is we run ourselves and we're like, this experiment's not working. It doesn't look like the mask actually stops performance. People or I'm much better at this than I should be. There must be something wrong with the program. You go down the hall and get somebody who's never seen this thing and you have them do it. And they're like, I have no idea what these objects are. They're totally a chance. And so
Yes.
you see, I mean, it takes a long time. We're talking weeks of practicing the masking task, right? To get it at that level. But we've seen crazy things in the laboratory like this.
So, Jeff, this is a really interesting discussion because in art tasks, there's no learning, right?
Wow.
And they're probably not encountering, no learning predating taking the task.
It's
right?
new to them. Yes.
There's no practice on
That's great.
corners of diamonds missing at these speeds.
Right.
And so we hear, like in baseball, for example, but there's other sport, tennis and all that. There are athletes that say, hey, I can see things so clearly and quickly out of the ball out of the hand.
Uh-huh.
The term is they see spin. They're seeing patterns produced by spin.
Yeah.
Much easier. And then there are other athletes who say, yeah, I'm not seeing that. I'm making judgments by the time my brain's figured out kind of what the exit, shape look like. So it's going to be a curveball if there's a hump out of the hand, and they're using extra information, or they're soft focusing like this and making a decision much later. But there are athletes who just say, I mean, we've heard athletes, they go in to work this system and they take these cannons and shoot tennis balls with numbers or letters marked on the faces of the tennis balls at 110, 120 miles an hour. And some players can see the numbers.
It's Barry Bonds type stuff, right?
Accuracy, but others can't. And so when we bring people into our perception speed, it is striking that there are athletes with no learning who just see things at these one frame mass delays with 100% accuracy, and athletes who don't achieve better than 50% accuracy or better than chance accuracy until they have a good 60 milliseconds between the stimulus and the mass. So what is the mixture? Some of this is innate and genetically kind of determined, but if we say you can train it, are there bumpers or ceiling effects? How far can you go? I'd love to have your thoughts on that, because that's a big question and discussion we have all the time.
The attentional focus issue I think that you're talking about is maybe where a lot of the movement lies in terms of these big differences between folks. In from about 1958 until the early 80s, attention researchers were mostly interested in one question, which is, does attention select the stuff it cares about before you recognize the object or after? So what, and so in the baseball example, this is, do you select, do you is attention like coming off the hand of the pitcher, or does, and at that location, and that's kind of what it critically does, or does attention really grab the thing, the ball, once it recognizes the good spin that it wants, right? Because, oh, that's fastball spin, that's the one I want. And so it's really kind of, does the smart part of your brain recognize everything and then grab the important things, or does it focus just on the early on one thing and then recognize the stuff that's in that focus? That was kind of the debate. Do you actually know what everything is and you just remember the stuff you attend to, or do you really only recognize the stuff you attend to and you can kind of filter out the objects that you're not attending to? Well, it looks like you can do both. We spent decades and millions of dollars, and we figured out the human brain can do both. And in an experiment I did in grad school, we showed that if you just have cues come up beforehand versus after the fact, you can get both. Early selection, that is, you just recognize objects if you're focusing at one location in space. You just recognize the objects at that location, and you don't recognize the objects out here. But you can not do that, not focus attention spatially when the information comes on, this kind of soft focus thing. The analog is the soft focus that you're talking about, where you just kind of, as some people say, let the stimuli come to you. Just like sit back and wait for it to happen, man. And that's effective in that you can recognize all of the objects, but you don't have that early benefit. So it looks like the brain recognizes the objects earlier if you attend to the location in space that it's coming off of. So presumably, if you could teach someone to shift spatial attention to the hand of the pitcher and come off of there, that is the optimal strategy. However, another strategy is to not focus there, right? Recognize the object, and then once you recognize it as, oh, that's a target, that's a fastball, then I need to try to figure out how to get my bat lined up with it to jack it out of the yard. So it's a different deal. And you of course would say like, oh, hey, it's much better to do it this way, to focus attention on that thing. But then you have to teach people to discriminate what those different motions are. The late selection strategy, that's what an attention researcher would describe this, the people who just let the stimuli come to them and recognize all the objects. Well, they are recognizing the objects and they are seeing the spin in some sort of way, but they might not have access to it, right? Which is like, oh, I just felt like I could swing at this one. Some people who aren't really, who don't give their brains much time to process the previous, iteration to know, okay, so that is a fastball. Now what do I need to do? That they instead seem to report some sort of kind of an emotional response to things. This is there's not a lot of data on that, though. Let me say that there's not a lot of data on that, but we do get it in masking experiments as well. So if you really ask people in a visual lab where they're doing masking experiments, well, did you see the object? And they're like, well, this is what I did. I pressed yes if I kind of felt like I saw it. And you're like, oh, Jesus. Because which is kind of how we feel like when we're swinging at a curveball. It's like, I kind of felt like this one wasn't spinning that much, or.
So what we're talking about, though, is actually kind of exciting, because we in the player development space, Jeff, we have two sort of paths.
That's exactly right.
We call these strategic adaptations, right? And that the example of that is the kid with low perception speed. He moves back in the batter's box to give himself a little bit more time, or off of the line of scrimmage to give him a little bit more time. The other one is true development, where it's like your monkeys in the lab, where you're literally training for hours. And in the whole cognitive rehab space or the development space, we've looked at perception and action coupling, and we have these transfer paths, particularly in baseball, about how to improve performance. And the first sort of layer of that is perception. So training the perceptual aspects of baseball and just taking rep after rep after recognizing pitches. Are you suggesting we have more room to actually train this, and
Yeah.
we should be spending time actually training this? And if that's the case, well, then we need to have a much larger discussion on what does that look like? I mean, how can we help our teams and our players get better at perception speed? Because it is a barrier. Kids with low perception speed struggle climbing the ladder in professional baseball. Kids with low perception speed, it is linked with defensive pass interference. It is linked with all sorts of things on the football field. How can we help these guys?
Yeah, this is a great question. First thing I think we should do is to get the cameras not where they are for game film. Like, why are we watching game film from where, not from the angle that the athlete actually sees the defense, but from where the birds are that are flying over the field?
So Jeff wants that Madden view, doesn't he? You want that Madden view.
Yeah, exactly. That is the only view anyway. Well, and I realize this because I always buy the cheap seats and go for the end zones. And I'm like, oh, this is the view I've missed since high school football. It's this is you can see the curvature of the field, the whole thing. So like the context specificity, and that's a science word for precision. That is exactly the time. Having it exactly the same. So having people like study game film that is actually of the view they're going to see. That would be a huge shift that I don't think we're actually kind of using right now. I mean, how Peyton was able to get all that out of all that game film study when he had to kind of imagine what it would look like. I mean, that's what our quarterbacks are doing right now, right? We're asking them to watch this game film, rotate it continuously in your mind, imagine what it looks like from your perspective, and so that you can recognize it when you see it that way.
They're changing that a little bit. They've got these projection rooms where they will project life size.
Nice.
And you line up in this room.
Yeah.
Some of the elite programs have these.
Really cool.
Actually
good.
Line up against the life size and the initial movements. You're exactly right.
Wow, that's perfect.
Keep going.
Yeah, and Doug does it in the VR space. Virtual reality that actually simulates.
Well, this is great. So there is a lot of movement to be had, and so that's kind of what you're training in. That is what are the pictures in your brain that you're matching to the perception coming in. A lot of the stuff we've been talking about is what cognitive psychologists tend to call perceptual learning. These are the most boring experiments known to man. They are of the kind I described with monkeys, but people do these with humans too. And here's the task, right? So you're going to see bars that are like upright, and then they'll be tilted like 1 degree to the left or to the right. And you have to say, is this right or left? Right or left? Is this right or left? Is this right or left? Is this right or left? And you just get a bunch of these, and they all look straight up to you. You're just like pressing the button randomly. You kind of get feedback across time. And what you find is that people get a little bit better during the day, but if they go home and sleep and then come back and do the task tomorrow, they're significantly better. And it looks like these are really important for these very low-level visual quantities. Let's say if you want to measure the tilt of a line and 1 degree matters. Well, that's kind of a dumb sports example because that never matters really. But if we get into direction of motion, now everybody's like, oh, that's hugely important, right? So there's your baseball and every ball sport, right, where the spin matters. And those sort of experiments where you're trying to detect a difference of a rotated spin that's this versus that, very small couple degree angular differences. Those are the sort of experiments where you see big gains with sleep across months. And so a combination of teaching people strategies and these low-level perceptual learning skills is probably the best move. Obviously, these sort of strategic things we've always just called coaching. It's just like, oh, that's good coaching. But you're really doing you're recognizing a cognitive limitation and trying to design a procedure for the athlete to get around it. I had to do it with myself, just for all the athletes out there. So I was a lineman, right? Offensive lineman. We got to remember a bunch of stuff. And I fancy myself as intelligent, like I'm a professor now, but I was not actually intelligent enough to be a lineman without a bunch of errors. So you have to remember the snap count and you have to remember the play and then what the audibles are, but that's kind of just the same until you get busted. But you have to remember the snap count and the play. And I realized, hey, these plays are kind of long sometimes. If I just put the snap count on my finger and I just hold my thumb to the finger that the snap count's on. So if it's my index finger, it's on 1. If my middle finger, and it's 2, ring fingers 3. And then I just code the snap that way. So it was a strategy so that I didn't have to hold that thing in memory. I would think about the play while I was walking up to the line, and then look at where my thumb was to see when I was supposed to go. Now, I'll tell everybody this too. There was one sneaky ass defensive lineman that noticed this one day and
Good
jumped me
instinctive
on
learning.
a play. And I was like, how did you see that? I wore gloves and the whole thing. But, that just shows how fast human learning can be too.
Must have been
right?
Myles
This
Garrett.
guy probably... Yeah, Myles Garrett saw it out of the corner of his eye.
Hey, Deion Jones popped into my head.
Yes.
Dude is an instinctive, picking up on subtle cues.
Yeah,
Yeah,
right.
you gotta notice.
Yeah, they feel the snap count.
So what I'm
Anyway,
hearing is
I'll
you
be
can do both the adaptive strategic, what we talk about coaching, the adaptive and strategic methods, and also there's a chance to developmentally move this needle in the confines of the sport that they're playing to get better at perception speed. Fascinating.
It's interesting, that if you talk to any coach and you say, yeah, you need to train your athletes to recognize pitches faster, they're going to say, yeah, duh.
Yeah.
The value in certainly S2's approach is to say, look, yeah, we've got to work on timing, we've got to work on pitch recognition, but there are principles and ways that we know work more efficiently. Decades of science, like you said, that can give us some guidance and help us, do this in a way that's going to be most efficient, that's going to be to maximize an athlete's capability of recognize pitches. And so Brandon, I think you're right. I think there's another conversation about what would this look like? What would a strategy and a set of, because we get all kinds of things you got people wearing strobe glasses and doing all kinds of things. It would be great to kind of dissect those and where could they potentially be beneficial? Where are they a complete waste of time? Because if there's one thing that we noticed right away in the sports world when we jumped into this was that the world after the decade of the brain was just inundated with brain training, and everybody and their dog was coming up with brain training gimmicks, gadgets, whack-a-mole boards, everything promising this is going to make you a better hitter. And that context specificity you talk about was so absent, so I think there's a lot to talk about in terms of what are the strategies to build faster, more efficient, leaner perceptual processing systems.
Oh man, we need to have Dr. Woodman on for another episode. What a fantastic thing and transition to have. Dr. Woodman, before we get into the last segment, I'd love to just hear about, I know you had mentioned something that you're working in your lab. What's new recently with your lab before we get to the last piece here?
Well, one thing I'm really excited about is I've been working with another memory researcher, and we've been trying to think through kind of what a unified model of memory would be. Human memory has turned into a little bit of a mess with people studying it in their own specific way, and so there's not a cohesive idea of like maybe human memory actually just works like this and it does these different tasks in these different sort of ways. So we're trying to bring some oneness. We'll see how this goes. People have tried to do that in the past. Brandon was probably involved in some of these exercises in his previous life, but that's pretty exciting. An interesting bit of being an academic and coming out of the pandemic is it actually left us with a ton of time to think. So we've been kind of acting on a lot of that, like
all the journals.
Deep thinking time.
Yeah, that's right. Okay, so next time you're on, we're talking about all these adaptive strategies and where to develop. We're going to get into where you got with the memory stuff in your lab. But now, for your favorite element of the show, if I can remember correctly, 3 random and funny questions. Are you prepared?
I think so.
Okay. Can you describe the craziest adventure you've experienced in your life? Could be a vacation, trip with friends, could be an upcoming trip with a certain person who's going to be helping out. I don't know.
Wow. These are great questions. Okay, the craziest thing I tried to do is I tried to fly into Hong Kong, give a talk, and fly out before my clock reset. And let me say, it was totally working. I hadn't slept for 3 days. I was on the outbound flight out of Hong Kong, and one of the engines failed on takeoff. And they diverted us to Tokyo, and they kept us in Tokyo for 2 days. And I basically slept for 2 days, and I arrived back in America totally on like a 12-hour reset. Total mess.
That fits the description.
Mistake.
Yep. Someone is being interviewed on TV or a podcast you're listening to. Who is the guest that makes you stop in your car, stay in your car, stop by the screen? Who's the guest that makes you want to listen to the full interview?
I think I'm going to say Hugh Jackman. He's got a lot of energy. And he seems to know how to do everything. Although I'm listening to the tragedy of Jeremy Renner, it seems like he also knows how to do everything. So I like people with diverse skills. So I'm going to say Hugh for now.
He can sing. He's got claws somewhere in his hands. Yeah, no, it's pretty amazing. And final question is your biggest pet peeve. What is it?
Oh boy. You know what it has been recently? Like I complained about it like over dinner with somebody, is the difference between less and few and less. It drives me nuts. I had to learn it because in Asian languages, it doesn't exist. So I have to teach it to grad students and postdocs and stuff. Like, okay, if it's a count noun, if it ends in an S, you use this one. And nobody else, no American knows how to use it. We just use less all the time because we think fewer sounds weird. And so like people are like, I have less dollars. I'm like, I'm going to kill you. So anyway, that's kind of my deal. I would say it's that thing.
So Scott, I see you nodding your head. Is this something you've thought about?
Yeah, it's not my biggest pet peeve by a long shot, but yes, I am aware of it.
It's a problem.
I had a mentor.
It's an issue. Yeah.
Thank you so much, Dr. Woodman, for joining us. We appreciate your time today. Can't wait to get into another discussion, the huge educational lift of what perception speed is, what does it look like in the lab on humans, and then, average Joes, and then to the athletes. We appreciate your time today. Thanks so much for joining us.
Thank you.
We hoped you learned a lot today about the intersection between perception speed or processing speed and how it reveals itself in a sports setting. Things that are happening quickly and how these athletes are able to process that at the point of focus is really what we focused on. Again, if you like the content we're putting out, please subscribe with that plus sign at the top, leave a review about the episode, and share it with a friend. If you'd like to get in touch with the show, please go to s2cognition.com/podcast. Thanks again for listening to the S2 Cognition Podcast. I'm your host, Harrison Hunter, signing off for now. Talk to you on our next episode.